Good evening, Lamai. Let's start this today's session. Today we are actually going to discuss about the precipitation reactions. Right, precipitation reactions. First, we'll follow those things, and then we'll follow how to complete the precipitation reaction and balancing the stuff. Right. Then we'll discuss about reactions, the calculations. Sorry, the calculations involved in the precipitation reactions. Right. Those are the things we are going to follow today. Right. So as you see, right, this is referred to as the precipitation table. So we are going to use the help of this thing to write the precipitation reactions, right? So first, let's try to read this stuff. How to read the precipitation table, right? You can clearly see some anions are appearing at this row, and at this column, you see the cations are there, right? So let's try to read this stuff, right? It is like this, Laman. So if you are to think of these cations, right, the NHO plus, the sodium plus, K plus, rubidium and the cesium ions, actually the group 1 ions and the ammonium salts, ammonium plus ions, you clearly see, right, with those columns, sorry, with those rows of these ions, you clearly see all the things are going to be soluble, right? If you think of ammonium oxalate, it is soluble. Ammonium hydroxide, it is soluble. Ammonium sulfate, it is soluble. Like that, all the salts of ammonium ion and all the salts with these group 1 cations other than the lithium are going to be soluble salts. You clearly see that trend with the precipitation table, right? So actually what we see is actually a trend of the group 2 guys. So when it comes to group 2 guys, there will be a variation of solubility and the precipitation, right? We can clearly see that trend appearing here. So let's discuss one by one, right? First thing to note that is all the ammonium salts and the group 1s other than the lithium are soluble, and in this block all these anions, the salts containing all of these anions are going to be soluble solutions, right? Not forming precipitates, right? Let's discuss about the precipitates now, right? That is our main goal here, to identify the precipitates, right, with the use of this precipitation table. Right, let's think, right, if you are mixing, if you are to mix, right, this kind of a thing, right, come to here, let's write here. So if you are trying to mix two salts, right, let's say you are trying to mix two salts like this, right, you are adding some magnesium sulfate and let's say you are adding some barium hydroxide, so sorry, barium chloride better. Let's say you are adding these two solutions together, right? Let's discuss how to use the precipitation table to come up with the reaction here. So if you are adding a magnesium sulfate and the barium chloride together, those solutions, see, a precipitation can occur or not. How to predict that using the precipitation table? It's like this, Laman. First, exchange the ions of these two salts. So that means the magnesium, the positive ion of this thing, check with the anion of the other salt, magnesium chloride. Is it a precipitate? The magnesium chloride, is it a precipitate? Just check here, magnesium, Mg2 plus sign is there, and the chloride, see, the X minus is about chlorides, right? Here the X minus appears with the halides, right? Cl minus, Br minus and I minus, right? So you see the magnesium 2 plus ion with the X minus sign. So the precipitation table says it's a soluble situation, no precipitate occurs. So magnesium 2 plus and the Cl minus combination won't give you a precipitate, right? Think of the other two guys, these two stuff, SO42 minus with the barium 2 plus, always the cations and anions. Those are the guys which will exchange between the guys. Barium 2 plus ion, here you clearly see, and the sulfate ion. Sulfate ion. See, you see the sulfate here. So sulfate and the barium 2 plus. You clearly stops at here. That means it's a precipitate, right? This 3 arrow situation is denoting you the precipitates, right? These are soluble stuff. These are precipitates. What I have colored, dark colored things are the precipitates, right? So sulfate combining with the barium 2 plus gives you a precipitate. So with this reaction, you would observe a precipitate, right? Which is actually what? Which is actually the precipitate of barium 2 plus and SO4 2 minus ions. So that is barium sulfate. So this precipitate appears. That is how you have to predict whether a precipitation occurs or not when two salts are to be mixed, right? This is how we use the precipitation table to predict that, right? Let's discuss about another two salts to mix, and let's try to predict whether a precipitation occurs or not using your precipitation table, right? See, if you have to mix, right, these two, see, if you have to mix some, right, let's come up with this sodium hydroxide. If you mix some sodium hydroxide aqueous solution with magnesium sulfate, see what would occur, whether precipitation occurs or not. Just check. So sodium with the sulfate ion, these cations from the one species combines with the anions of the other species. That is how we are check, right? Sodium sulfate. So sodium, you clearly see sodium is not going to form any kind of a precipitation. All the sodium salts are appearing as soluble stuff. No precipitation with all the sodium salts. See, all are soluble. So there's no precipitation from here. There's no precipitation from here. Let's check for the other stuff. Magnesium with the OH minus. Magnesium with the OH minus, right? See, magnesium 2 plus ion with the OH minus. See, here and here, OH minus, right? So OH minus and the magnesium 2 plus. See, those will stop here. That means it's a precipitate. It's a precipitate. See, so magnesium hydroxide is a precipitate. So you would observe a precipitation here, and it is what? It is the magnesium hydroxide. So it is actually the magnesium hydroxide. That is how you're supposed to predict a precipitate with the use of precipitation table. Clear, no? That is how we are supposed to use this precipitation table to predict a precipitate, right? Okay, right. Let's discuss more about this precipitation table, right? Let's discuss about the patterns of this precipitation table, Lama, before going for the calculation questions. Let's discuss a few of the patterns available appearing with the precipitation table, right? Okay, let's come up with one by one. First thing note that is, right, the ammonium salts and the group 1 cations other than lithium won't precipitate, never precipitate. You see, no precipitation appears with those cations. Ammonium salts and the group 1s other than lithium never get precipitated, right? No precipitation with those, right? Then these anions, the halides, sulfides, nitrites, nitrates, MnO4 minus, manganate, bicarbonate and the dichromate, these ions never form precipitates with the S-block cations. With S block cations, you won't see, right, the precipitation appears with these anions as well, right? Those are the first two things to note, right? Then let's discuss about one by one the anions, right? Basically, when it comes to S block, the group must never get precipitated. When it comes to group 2 guys, right, you can see some precipitation trends, right? So some special trends can be seen here. When it comes to hydroxides, the top two guys of the group 2, the beryllium and magnesium, those are the only ones which get precipitated at this block for the hydroxides, right? When it comes to hydroxide precipitation trend, top two guys of the group 2 will get precipitated as hydroxides, right? Okay. So when it comes to sulfates, the bottom two of the group 2 will get precipitated, right? So such kind of a trend is there with the hydroxides and the sulfates, right? When it comes to hydroxides, the top two of your group 2 get precipitated as hydroxides, and when it comes to sulfates, the bottom two of your S block will get precipitated as sulfates, right? Few more trends, few more stuff you should know about these precipitation trends, right? What are those, right? Let's discuss a bit more about the hydroxide precipitations, right? So when it comes to hydroxide precipitation, OH minus hydroxide precipitation, right? These things should be mentioned, right? So from S block, right? From S block, only magnesium 2 plus and beryllium 2 plus, only the beryllium 2 plus and magnesium 2 plus get precipitated as hydroxides. But if you have to think of P and D block metal cations, if you think of P and D block metal cations, all the metal cations will precipitate as hydroxides, right? So all P and D block metal cations precipitate as hydroxides, right? That is the hydroxide precipitating trend, right? So from the S block, only the beryllium and magnesium will get precipitated as hydroxides, but when it comes to P and D block metal cations, all of them will get precipitated as hydroxides, right? Like if you think of zinc 2 plus, it will get precipitated as zinc hydroxide. Iron 3 plus, iron 2 plus, those will get precipitated as hydroxides, right? Not only those, the aluminium as a P block cation, aluminium will get precipitated as aluminium hydroxide, right? So when it comes to P and D block cations, metal cations, all of them will get precipitated as hydroxides. Only in S block, the hydroxide precipitation is weak. Only the beryllium and magnesium will get precipitated. But with all the other two blocks, P and D blocks, right, hydroxide precipitation is very severe, and all these metal cations will get precipitated as hydroxides, right? That is what you should know about the precipitation trends of hydroxides, right? Okay, let's discuss about the precipitation trend of sulfate as well, right? Sulfate precipitation, what you should know, right? What you should know about the sulfate precipitation, right? When it comes to precipitation of sulfates, right? Precipitation of sulfates, what you should know. Actually, right, in our A-level syllabus, only 3 cations are capable of forming sulfate precipitates. Only 3 cations are capable of forming sulfate precipitates. What are those? Only these 3 guys, Lamai. right? You can clearly see two of them appearing here with the precipitation table here, sorry, here. So that those are strontium sulfate, the white PPT, right? Then you have barium sulfate, again a white PPT, and then the next one is lead sulfate, again a white colored PPT, right? As sulfates, only these three are available as precipitates in our A-level syllabus, right? When considering A-level syllabus, right? Only these guys will appear as precipitates, as sulfates, right? Okay. So you can clearly see two of them appearing with this block table, and lead is also capable of forming sulfate precipitation, right? Okay. Only three of them will appear as sulfate precipitates, right? Okay. So basically, when it comes to chromates, let's discuss about the chromates trend now. When it comes to chromates, chromates normally follow the precipitation trend of sulfates. Chromates will follow the precipitation trend of sulfates, right? See, so as chromates as well, then the strontium, barium, and lead will precipitate as chromates as well, right? So when it comes to chromate precipitation, right? Chromates also follow the trends of sulfates. Let's write that thing as a precipitation of chromates. Right, basically they follow it follows the trend of sulfates, right? So what are the chromate precipitates available then? So those are strontium chromate, barium chromate, and the lead chromate, right? Those are the major three stuff. Other than that, right, silver chromate is also appear, right? Only 4 precipitates are available as chromates: strontium, barium, lead, like in sulfates. Those 3 ions are there, and silver chromate. Those are the only 4 precipitates available as chromates, right? Okay, that is the trend of trends what we can see with the chromates, right? Let's discuss about the sulfides, right? Basically in S block, right, the bottom three will appear as sulfates, right? So calcium, strontium, barium will get precipitated as sulfates. For carbonates, normally bottom 4 at the S block will precipitate the carbonates, and when it comes to phosphates, all the guys at the group 2 S block get precipitated as phosphates, right? That is the normal trends what we can see with the precipitation table. And when it comes to oxalates, that is also a special trend we can see. Only the right calcium and strontium will appear as precipitates for the oxalates, right? These are the things appearing with the precipitation table, right? Main stuff in the precipitation table, right? So other than the stuff appearing at the precipitation table here, we need to know a bit more data when it comes to precipitates, right? Let's discuss a bit more about the halogen precipitation, right? When it comes to a precipitation table, you won't see any kind of halogens precipitating here, as we are concentrating only on the S block here with this precipitation table, right? No halogen precipitation with the S block cations, but few halogen precipitates are available with the P and D block cations. Let's discuss about those things as well to have a complete idea about the precipitates, right? Let's discuss about the precipitations with chlorides, right? Okay. See, precipitates with chlorides. Okay. So I'll erase this one now, right? Let's try to come up with chloride precipitation. right? Chloride precipitation or halides. Halide precipitation. Now, in S block, no one will get precipitated as halides, right? In S block, no cation will precipitate as halides, right? But when it comes to P and D block, only 4 cations are able to precipitate as halides, right? Only 4 cations are able to precipitate as halides. What are those? Right? These are the ones. Silver is capable of precipitating as AgX. AgX means it could be AgCl, AgBr, or AgI, right? X representing the halides, right? So, other guys, you can think of PbX2 precipitation, lead chloride, lead bromide, and lead iodide. What else? So, you can think of mercury precipitating as halides, HgX, that means mercury chloride, mercury bromide, and mercury iodide. And Cu1 plus, Cu1 plus is also capable of precipitating halides, CuX, Cu chloride, copper iodide, copper bromide, like that, right? Those are the only 4 cations which are able to get precipitated as halides, right? So that is some additional data you should know other than the precipitation table of S block cations, right? So all of these things are appearing in your note, Lamai, at the page number 14 of your tute. You can clearly see these notes, right? Okay. So this is all what you should know about the halide precipitation, right? Idea is clear now, right? Okay. Let's discuss bit more about this stuff, right? Bit more stuff, right? You should know. Okay, let's do this stuff. So how to predict? Right. First exchange the ions and see whether precipitation occurs or not. Right? See? Sodium plus with Cl minus. Sodium plus with Cl minus. Right? Group 1 guys never get precipitated. Group 1 guys never get precipitated. No precipitation there. Right? These two guys. PO4 3 minus ions with calcium 2 plus. When you are seeing the precipitation table, all the group 2 cations will get precipitated as phosphates. At the right corner, you could see the phosphates appearing. So all the group 2 guys will get precipitated as phosphates. So there will be precipitation from here. There will be precipitation from here, right? So there's no precipitation from here. See? Let's try the equation here. Let's try the equation there. Right? So sodium phosphate with calcium chloride. Sodium phosphate with calcium chloride. So I'll write it here now. So I see some. Not space is enough there, right? So sodium phosphate is calcium chloride. Sodium phosphate with calcium chloride. So how to write the reaction? Basically, my precipitation reactions are referred to as, right, ion exchange reactions. Precipitation reactions are always referred to as ion exchange reactions. Just exchange the ions and write. Sodium plus comes with Cl minus NaCl plus calcium 2 plus comes with the anion of the other species, calcium phosphate. Calcium phosphate. Right? Calcium 2 plus, so 2 plus here, phosphate 3 here, right? So sodium chloride and calcium phosphate. Those are the products, and this is your precipitate. This is your precipitate. I'm indicating the precipitate with this sign, right? So just balance the stuff, right? So using the precipitate, you can balance the stuff, right? So you have 3 of calcium ions and 2 of phosphate ions. Then you will see 6 of sodium plus appearing with 6 of Cl minuses, so 6 here. This is the balanced chemical reaction for the reaction between sodium phosphate and the calcium chloride, where you get the calcium phosphate as a precipitate, right? No? Okay, let's do the second one. Right? First check whether precipitation occurs or not, right? Nitrates never get precipitated, right? So no precipitation from nitrates in the K plus, but barium 2 plus connecting with sulfate gives you precipitation, gives you precipitate. Barium 2 plus with the sulfates, yes, it's precipitate. You know that only 3 sulfate precipitates are available now. One of those is coming from the barium, strontium sulfate, barium sulfate, and the lead sulfate. One of those sulfate precipitates are coming from the barium. So this is precipitation there. So just write the reaction. So barium nitrate reacting with K2SO4 to produce what? Just write the two products. Barium 2 plus coming up with sulfate. So barium sulfate, that is your precipitate, plus the other solution, K plus coming up with the nitrate, K plus and NO3 minus. So K plus and NO3 minus. So plus and minus, right? So balanced, right? K NO3. That's the solution, right? So let's balance this stuff. We need to balance the stuff, right? 1 barium and 1 sulfate is appearing. So 1 sulfate, 1 barium. So to balance the K plus and the nitrates, so you have 2 of nitrate groups. So need to come up with 2 here. 2 of K pluses and 2 of nitrates, right? Thing is balanced, right? Okay. Let's check for the precipitation here. So K plus never get precipitated. Group 1s never get precipitated, right? So no need of comparing with its chlorine, right? And then check these two guys. Yes, there's a precipitation there. OH minus with the Mg2 plus. Yes, magnesium hydroxide is kind of a precipitate, right? So let's write the reaction there, right? With the KOH reacting with the magnesium chloride. KOH with the magnesium chloride. So how to write the reaction? First, K plus coming up with the anion of the other species. So KCl, K plus and Cl minus, KCl, and here OH minus and the Mg2 plus, OH minus and the Mg2 plus, right? So Mg2 plus and the OH minus. So magnesium's valence is 2, so that should be written with the OH minus, and OH minus valence is 1. So that is written with here. So MgOH2, this is your precipitate. So just mark the precipitate like this, right? In your reaction. Okay. Then now the balancing. With the use of the precipitate, just balance. 2 of OH minus should be there. So you have to count with 2 here. Write 2 of OH minuses and 1 magnesium. Yes, it is 1, right? Okay. So with this, you can clearly see 2 of K pluses are available and 2 of Cl minuses are available. So 2 of KCl should be the balanced reaction, right? Okay, right. Those are the balanced reactions for the first 3. Let's copy the next 2 as well, right? This one, NaCl combining with the silicium. So Na plus never get precipitated, no need of concern in that. Let's consider about the other 2. Cl with the Ag plus, Cl with the Ag plus. When it comes to halogens, only 4 cations are able to get precipitated as halogens. Out of those 4, Ag is one such a cation, right? So Ag plus will get precipitated as AgCl here, right? So there's a precipitation. So we need to write the reaction, right? So let's come to the reaction. So NaCl reacting with silicium. So write the products. So Na plus combining with the NO3 minus here. So that is NaNO3 plus Ag plus connecting with the Cl minus, that is AgCl. So that is your precipitate. This is your precipitate. Things are balanced here, right? Okay. Next one. This thing. Magnesium nitrate with the sodium sulfate. Right? Let's see whether a precipitation occurs or not. Magnesium. Magnesium should try to connect with sulfate. So magnesium sulfate, is it a precipitate? No. Magnesium, basically when it comes to sulfates, right, the bottom two will get precipitated as sulfates, right? The bottom two will get precipitated as sulfates, the strontium and barium, not the magnesium. So that is not a precipitate, not going to be precipitate. What about these two? Sodium plus and nitrate. Sodiums never get precipitated as well as nitrates. So no need of concern in this. So actually no precipitation there. No precipitation, right? No precipitate. No PPT. So if you have to mix magnesium nitrate solution and a sodium sulfate solution, you won't see any kind of precipitation appearing, right? So it's a no precipitation situation, right? That is what you, that is how you are to write these reactions, right? If a reaction occurs, if a precipitation occurs, you need to complete the reaction and balance the stuff. And if there is no precipitation, no need of writing any kind of reaction here, right? Okay, so that is how you're supposed to come up with the balanced chemical equations regarding precipitation, right? The things are okay, no? Right. Okay, let's discuss about few more stuffs you should know about the precipitation. Right, let's discuss the note appearing at the bottom part of the page number 14. Right, there is a note appearing at the bottom part of the page number 14 after your precipitation table. Let's discuss about the theory behind that note, right? That is very important in calculation stuff, right? Let's see what it says. It says it is this kind of stuff, right? So if you think of precipitates, right, we can discuss about the dissolution of those precipitates in acids, right? Let's discuss about that thing, right? The special note, right? Special note. Here we are discussing about, right, dissolution of precipitates. Dissolution of precipitates, right, in acids or in acidic solutions. This is what we are going to discuss here. Under this, we should know about two things. What are two things? It's like this. It says if the precipitate contains an anion derived from if a precipitate contains an anion derived from a strong acid, that means if you are with some Cl minus, Br minus, I minus anions or some sulfate anions, if you are with these anions in your precipitate, then such precipitates won't dissolve in dill acids. See, this is the idea. It's like this. So see, you are with a barium sulfate precipitate. You have precipitate the barium sulfate. The idea is, if you add kind of a acid, say HCl is added, some acid, this point says the precipitate won't dissolve. The precipitate won't dissolve. So if earlier you had X moles of barium sulfate precipitate, after the addition of dill acid, still X moles remain. Precipitate won't dissolve. That's what it says. If you are with a precipitate with any of these anions, then such precipitates are not going to dissolve in dill acids. Right? That is the idea. See another example. Say you are with some precipitate AgCl, right? And you are adding some acid, your nitric, another dill acid. This theory says that your precipitate won't dissolve, still stands. Right? If X moles were there or Y moles were there as a precipitate, still that Y moles will be there as a solid precipitate. That won't dissolve. Even a bit of that stuff won't dissolve. That is what this says. It's very important now, yeah. So we'll discuss the applications of this thing, right? First of all, keep it in mind, if a precipitate is with a strong acid anion, sulfate, fluoride, even the lead sulfate, strontium sulfate, lead chloride, mercury chloride, those stuff. If a precipitate which is a sulfate or a chloride anion, some strong acid anion, right? Those won't dissolve with dill acids in acidic mediums. So this is acidic medium, right? So you are now seeing a acidic medium here. Still, your precipitate stands, won't dissolve. This very special thing happens with the precipitates containing strong acid anions. So that is one thing you should know. If a precipitate is with a strong acid anion, that won't dissolve in dill acids, right? Then the next stuff, the next thing is about the precipitates without strong acid anions. The precipitates without strong acid anions. Let's discuss about that thing as well. The second point, right? If the precipitate is not with a strong acid anion, if the precipitate is not with a strong acid anion, that means not with SO42 minus Cl minus Br minus I minus anions, then such precipitates will dissolve in dill acids, means acidic mediums. See what it says like this. Say you are with a magnesium hydroxide precipitate. Say you are with a magnesium hydroxide precipitate. Here you are with OH minus anion. It is not a strong acid anion. It is not coming from H2SO4, HCl, HBr, HI, right? It's not a anion coming from a strong acid, right? So if you add some del H plus here, let's say del HCl, then what will happen? Actually, this one will dissolve. This one will dissolve. This one will dissolve, right? Forming what? Forming magnesium chloride. Forming magnesium chloride and H2. Magnesium chloride and H2. That thing will dissolve, right? So in acidic medium is acidic. Magnesium hydroxide dissolves, right? Precipitation won't appear. Let's come up with another example. See, say you are with some carbonate, calcium carbonate. You are with calcium carbonate precipitate. And let's think you are to add some acid there. Literally even, right? Some acid. Nil acid. So what will happen? So the calcium carbonate will dissolve. Calcium carbonate will dissolve. Forming what? Salt. Calcium nitrate. It will dissolve forming calcium nitrate. Aqueous solution. Right? Calcium nitrate aqueous solution. It will dissolve, right? That's it. So you have acidic medium. So they are calcium carbonate dissolves. Right? So precipitate won't appear in acidic mediums if a precipitate won't contain a strong acid anion. If a precipitate won't contain a strong acid anion, right? Precipitate will dissolve in acidic mediums, right? That is very important. Note that, right? All the hydroxides, carbonates, phosphates, sulfides, not the sulfates, sulfides, oxalates, even the chromates, all the precipitates other than the sulfate and halide precipitates will dissolve when you are to add a dill acid to it, right? This is very important to note, right? Let's discuss about some practical application of this theory, what we have learned now. So some practical application there. See. Right, I'll come with some example. This is some example. So let's say you have this kind of a procedure to find out the concentrations of sulfite and sulfate ions in an analyte solution. Right. Let's say that you are with kind of an analyte solution where you are with SO32 minus and SO42 minus ions, and let's say you are with 25 cubic centimeters of that thing, right? So you need to come up with the concentration of SO3 2 minus and the SO4 2 minus ions in this solution, right? That is your goal here. That is what you should achieve here ultimately, right? So you can come up with this kind of a procedure to achieve the goal, right? So first you can add some kind of barium chloride solution, some barium 2 plus ions, right? Yeah, as barium chloride, no worries, right? So you can add this thing as barium chloride solution, right? Then what will happen? If you add barium 2 plus ions, precipitation tables is that barium sulfide as well as the barium sulfate, both the things will get precipitated. Right? That is what precipitation table says, right? The barium sulfide as well as the barium sulfate, both will get precipitated as you add in barium 2 plus ions, right? So our task is to come up with the concentration of this thing. So to come up with the concentration, if you are able to come up with the number of moles here and here, that will be done, right? That is our task, right? So if you know the number of moles, you can come up with the concentration, right? So see, if you have to come up with this kind of a precipitation, if sulfite amount is x moles, barium sulfite amount will be also x moles, right? Because you are not to get rid of SO3 2 minus ions from the flask, or you are not adding any SO4 2 minus to the flask. So the same amount of sulfides at the initial flask should be appeared at the final flask as well. So sulfite moles is x moles, so the barium sulfite amount should be x moles. So sulfate moles is y moles, so barium sulfate amount should be also y moles to conserve the mass, right? So let's say you can weigh this mass here as m1 grams. If you are to weigh this mass as m1 grams, right? So we can come up with some simultaneous equation. We come up with a simultaneous equation for mass of precipitate 1, right? It will be the summation of masses of barium sulfite and barium sulfate. So if the molecular weight of barium sulfite, let's come up with that thing. The molecular weight of barium sulfite is 217 G mole minus 1, and the molecular weight of barium sulfate is 233 G mole minus 1. You can write the mass of a precipitate as 217x plus 233y, right, which will be equal to m1, right? Now the mass of precipitate so includes the mass of this thing plus this one. If you are with x moles of the barium sulfite, its molar weight is 217, so that 217 G mole minus 1 into x moles will give you 217x. That's the mass of barium sulfite. And the mass of barium sulfate is going to be like that, 233 into y, right? That is the equation number 1, right? Equation number 1. So if you need to complete solve for this question, solve for 2 unknowns, you need 2 equations, right? So we can use right the theory what we have learned just now, right, to come up with the second equation, second simultaneous equation. What is that? Just to add an acid, right? Just add an acid here, right? Just add some DLH plus, right? In the form of HCl or HO3, you can add some DLH plus. So what will happen then? So if you are to add DLH plus, barium sulfite will dissolve. As it is not with a strong acid anion. As barium sulfite is not with a strong acid anion, it will dissolve, while the barium sulfate will stand. So only the barium sulfate will stand, right, as the precipitate, right? But the barium sulfide will dissolve, right? Barium sulfide will dissolve. That means dissolving means barium 2 plus ions and sulfide ions will be given to the solution, right? So if you can weigh this mass as M2, you can come up with the second simultaneous equation from here, right? As only Y moles are appearing here. For the mass of the precipitate 2, you can write Y moles into its molar weight, that is 233, that will be equal to M2, right? So this is the mass of precipitate 2. So you can combine these two guys to come up with the X and Y. As we know these values, M1 and M2 are known values. You can weigh those values. So combining M1 and combine the equation number 1 and equation number 2, right? You will come up with the simultaneous equations. By solving two simultaneous equations, you can come up with the X and Y, right? Okay. So you can write solving equation 1 and 2 will give the number of moles of SO32 minus and SO42 minus initially at 25 cubic centimeters. So that will lead you to the concentration. This is our solution, right? With this data, you can come up with the concentration, right? So here, what we have used is actually the theory what we have learned. The precipitates which are containing weak acid anions, so not containing strong acid anions, will dissolve in dilysis, while precipitates with strong acid anions stands, right? And adding here barium sulfide will dissolve as it won't contain a strong acid anion, right? That is what happens here. By addition of DLH plus, right? So this is the idea. So with the use of these techniques, we can come up with the two simultaneous equations, right? Which will be ultimately to solve the question, right? That is the usage of dissolving the precipitates in acids, right? This will be also very helpful when some extreme, the hard questions are involved, right? Okay. So we had completed actually the theoretical background. We should know about we should know to solve precipitation questions, right? Precipitation calculations. Let's try to use them in calculation questions. Right, Lama. Let's try to solve this question. This is a question, right, which is related to precipitation, right? This is actually the question number 2 appearing in your page number 17. Let's try to do this stuff, right? Okay. So here as well, we are using the same problem solving technique, right? So last few weeks we had discussed about this problem solving technique. So what is the first thing to do? The first thing to do is actually identifying the goal. Identifying the goal and put X moles, Y moles, the unknowns, to the chemical species related to the goal, right? Okay. So what is the goal here? Basically, when you are to go to the question, you clearly see the goal is this: find out the percentages of sodium chloride and calcium chloride in the solid sample. So that is the goal. Find the percentages of NaCl and CaCl2 in your solid sample. That is the goal, right? So goal is on sodium chloride and calcium chloride. So identifying the goal, that means you can write like this: let the sodium chloride amount is equal to X moles and calcium chloride amount is equal to Y mole in 5.67 grams of sample. So that is identifying the goal, right? First thing is to identify the goal. Second thing, then you are supposed to come up with the balanced chemical reactions related to the procedure. Balanced chemical reactions related to the procedure. See what kind of a process you are doing here. So basically what you are doing here is, right, you have a solid sample containing sodium chloride and calcium chloride. Excess amount of AgNO3 solution was added. So it's like this, no? You had a solid sample containing sodium chloride, right? You had a solid sample containing what? Sodium chloride and calcium chloride. Sodium chloride and calcium chloride, right? So we had taken the numbers there as X moles and Y moles, right? The sample is with 5.67 grams, right? You have added what? The AgNO3 to it. AgNO3 to it, right? See, then what will happen? They are saying that, right, some dry mass of the precipitate obtained was given, right? So what would be the possible reactions here? What would be the possible reactions here? So you have to select that. So first of all, think of the solution you are adding from the top. Basically, nitrate ions never get precipitated. Nitrate ions never get precipitated. Never get precipitated, right? So Ag plus is the one we have to think of when it is to considering as precipitate, right? Okay, no use from the nitrate ions, right? When it comes to the species at the solution, Na plus never get precipitated. Na plus never get precipitated. As nitrates are not going to precipitate, no use of Ca2 plus, right? Ca2, if the Ca2 plus is to combine to have a precipitate, we should combine with the anion of the other species, no? Anion of the thing what you are adding, no? Right? Anion and the cations will get combined, no? To form precipitates. So as nitrates are not in use, not of any use, right? So cations of the things at the flask, right, can't involve in precipitation, right? So no use of Ca2 plus as well here. So the two precipitations appearing here is the AgCl from this one as well as AgCl from this one, right? So first write the two reactions involved in the procedures, right? So procedure. So you clearly see this thing will get precipitated with this solution as Cl and Ag plus will get precipitated. Not only that, this solution will get precipitated with this thing as well, as here also Cl is appearing. So let's write the two equations then. So the first equation is between AgNO3 and the NaCl. What is the precipitate? The AgCl is the precipitate. AgCl is the precipitate, and NaNO3 will be there at the solution. So it is balanced, right? Thing is balanced. But NaNO3, sorry, Na. This cation comes with the anion of this thing, AgCl and NaNO3, right? What about the other thing? AgNO3 reacting with calcium chloride. There, AgCl will get precipitated, and the two other ions, calcium and nitrate ions, right? So calcium nitrate, CaNO3 twice, Ca2 plus, no? NO3 minus, right? Okay. So those are the two precipitates appearing here, right? So first of all, you need to balance the two reactions when writing the reactions, right? So let's balance the stuff, right? So just one Ag and one Cl will appear, right? But two Cls are here. But when it comes to the salt, you clearly see two nitrates are appearing. So put some 2 here. So that you need 2 of AgCls, no? Okay. So these are the two balanced chemical reactions, right? So you are with X moles of NaCl and Y moles of calcium chloride. We are with those, right? Okay, right. Balancing chemical reactions, that is done, right? Okay. Third thing, coming up with the simultaneous equations with the use of data points. Actually, what are the data points available here, Lama? What are the data points available here? The data points available. So the two data points available here are 5.67 grams. That is the mass of the solid sample. There is one data point. See this value, right? Mass of solid sample, right? Mass of solid sample. In terms of grams, we can write the simultaneous equation. What is the other data point here? Other data point appearing here is the mass of the precipitate. Mass of the precipitate, right? This is about the mass of precipitate. So what is precipitate? That is here. See, that is here. Here is the precipitate, right? That is the second data point. This is the second data point, right? Second data point is about mass of precipitate. Here it is the AgCl. In this case, it is only the AgCl, right? So in terms of grams, data point is given in terms of grams, right? Okay, let's come up with two equations here. Two simultaneous equations here. Mass of solid sample. To convert the number of moles to grams, right? You need to multiply it with its their molecular weights, right? So that we need to come up with molecular weights first of all. So molecular weight of NaCl, that is 35.5, and 23, that is 58.5. What was the molecular weight of calcium chloride? So you have 40 here, 2 of 35.5, that is 71, and 40 is 111. With these, we can come up with the masses. The mass of sample is actually mass of NaCl plus mass of calcium chloride. Mass of NaCl is the number of moles into its molar weight. So 58.5 x plus the mass of calcium chloride is its molar weight into its number of moles, that is 111 by, that is equal to the data point, the mass of sample, that is 5.67. That is equation number 1, right now. Okay, let's come up with the equation number 2. This one, mass of precipitate, right? First of all, To get the mass of precipitate, which is AgCl, first you need to know the number of moles of AgCl as well as the mole weight of AgCl, right? Let's copy the number of moles as you have with X moles here. The same X should appear here as well, because 1-to-1 ratio. As you have with Y moles here, it's going to be 2Y moles. Clear? No? 1-to-2 ratio, Y moles means 2Y moles. So total amount of moles is X plus 2Y. That should be multiplied with the G mole minus 1 value to come up with G here, right? First of all, let's copy the G mole minus 1 value for the AgCl. So Ag is 108, Cl is 35.5, so 143.5, the G mole minus 1 value. So you can copy the mass by just multiplying the number of moles with G mole minus 1 value. The number of moles is X plus 2Y. The number of moles is X plus 2Y. The G mole minus 1 value is 143.5. So you can write it as 143.5 into X plus 2Y. G mole minus 1 value into moles. So, right, mole minus 1 will cancel off with the moles and you will get the number in grams, right? That is equal to what? The data point. It is given as 14.35. Right? So if you are to simplify this thing, so if you divide this whole equation by 143.5, you will get the number as X plus 2Y is equal to 0.1. That is the second simultaneous equation. So you now has came up with two simultaneous equations, right? Now what we need to do is just solve for the two unknowns. Right? Let's try to solve for the two unknowns, right? Okay, let's do the stuff from here, right? Solving for two unknowns. X and Y. Solving for X and Y. Right? So I'll solve from here now. So I am lack of space here, right? So I'll come from here. So solving for X and Y, right? Okay, so we have the two equations like here and here, right? So what we can do, let's multiply this second one from 58.5, right, and minus the first one. That will get rid of X, right? That will get rid of X, right? What I'm doing is just multiplying the second equation by 58.5 to get rid of X, and that will be that first equation will be deducted by the second one, right? So reduce number one, right? So then what will happen? So 58.5 and the 58.5 here will cancel off, and with the second equation we'll come up with 2y into 58.5 is kind of 117y, right? That's it, no? Right, 117y minus the first value 111y, that is equal to this into 58.5 is 5.85, that minus 5.67, that will give you 6y is equal to 0.18, right? So y is equal to 0.03. This solved for y. So apply this value to equation 2. From 2 you will get the x value as 0.04. So we had solved for x and y. Then what we need to do, just to come up with the mass percentages, right? Okay, we had solved for x and y. Now they're achieving the goal, right? Now we're achieving the goal, right? What we can do, so we can come up with the mass of NaCl as well as calcium chloride, right? So mass of NaCl, first of all, NaCl mass, right? So that will be given by what? NaCl mass will be given by, right? I'll write it here. You have 0.04 moles, right? And the mole weight is 58.5, right? So the mass there will be, right, 58.5 into 0.04. So 2 of the 58.5 is 117. So 234. So need 2 decimals, no? 2.34 grams, right? So then we can copy the percentage. That's going to be 2.34 grams divided by the total mass. It is 5.67 into 100. So the value is going to be, let's simplify this stuff now. 3 point is 2.34 divided by 5.67. That is 41.26. So this is the percentage of NaCl. As only NaCl and calcium chloride are appearing in the solution or in the mixture, we can come up with the calcium chloride percentage as 100% minus the NaCl amount, because only those two guys are available. So that will be given as 58.74. Right now, that is how we are supposed to solve this kind of a question, right? Just copy it down. Okay, now let's try to do the question number 3 appearing in the page number 17, right? This is also regarding the precipitation reaction, right? Let's try to solve this one. See, first thing is to come up with the goal, identifying the goal properly, right? So here, basically, at the end, they are asking you to find out the concentrations of sodium phosphate and sodium sulfate in the stock solution, right? That is your goal, right? So finding out the concentration of sodium phosphate and the sodium sulfate in the stock solution, that is your goal, right? So these are the two chemical species related to the goal, right? So let them as x moles and y moles, right? So just write that thing. Let the amount of sodium phosphate as x moles and the amount of sodium sulfate as y moles, right? In actually in 25 milliliters. In 25 milliliters of the solution, right? You had taken only 25 centimeter cubes there, right? In 25 cubic centimeters of stock solution. right? That is identifying the goal, right? Then let's try to come up with the balanced chemical reactions. So next task is to come up with the balanced chemical reactions here, right? See what is happening here first of all, right? So you had a stock solution containing aqueous sodium phosphate and sodium sulfate, and you had taken 25 milliliters out from there. So it's like this. So you had a 25 cubic centimeters of your stock solution. Now there you had the sodium phosphate and sodium sulfate, right? You had taken the amounts there as x moles and y moles, right? And then what you have done, you had just added the barium hydroxide. You had added the barium hydroxide solution to your 25 cubic centimeter solution, right? So what is about the consumption of barium hydroxide? It was 20 milliliters of 2 mole solution. That is the consumption of barium hydroxide to totally react with the stuff appearing in the solution, right? So this is the picture, right? So let's try to come up with the balanced chemical reactions out of this procedure, right? First of all, right? Let's concern what are the precipitates could be formed with this procedure. So if you think of this solution, barium 2 plus as well as hydrox OH minus both can get precipitated. Two ions both can get precipitated. But when it comes to the solution, right? Comes solution, sodium plus ions never get precipitated. Sodium plus ions never get precipitated, as well as these sodium pluses. So that no use of the anion here. If all the cations at the solution are not going to precipitate, no use of the anion of the solution as well, right? So then what are the precipitates available? Let's predict. Barium 2 plus, is it going to precipitate with the phosphates? Barium 2 plus, is it going to precipitate with the phosphates? PO4 3 yes. Our precipitation table says all the group 2 cations get precipitated as phosphates. So barium 2 plus will precipitate as phosphates. What about sulfates? Our precipitation table says the bottom two cations of the group 2 will get precipitated as sulfates. So bottom 2, that means strontium and barium, those guys will precipitate as sulfates. So both of these ions are able to precipitate with barium 2 plus ions. So both of these guys will react with the barium hydroxide same, right? Okay, let's try the two reactions then, right? So two reactions. So sodium phosphate reacting with barium hydroxide. Let's try to let's try to balance the stuff. Sodium hydroxide and barium phosphate. Let's try the precipitate. That's better. Barium phosphate. So how to write the barium phosphate? The chemical formula. Barium 2 plus. So the variance valency comes with the phosphate ion. PO4 3 minus. That valency comes with the barium ion, right? This is the precipitate. Plus the other two. Sodium plus goes with OH minus. These two and these two, right? This is how the precipitations are concerned. So just ion replacement reactions. Sodium hydroxide, right? NaOH. Just try to balance the stuff. You have 3 of barium 3 plus. So barium 2 plus, 3 of those. So you have to come with 3 here. So you have 2 of phosphate ions. 2 of phosphate ions. So you have to come with 2 here. 2 of phosphate ions, right? Okay. So to balance the sodium hydroxide, you have 6 of sodium plus ions and 6 of OH minus ions. That means you need to come with 6 of NaOH, right? So that is the first balanced chemical reaction. That's the reaction with the sodium phosphate for the barium hydroxide. Then we have to write the reaction with the sodium sulfate as well. Let's write this stuff as well. Sodium sulfate with barium hydroxide, right? let's consider the two species, these two guys and these two guys, no? So barium sulfate is a precipitate here. Barium sulfate is the precipitate, and the other ones sodium hydroxide. It's balances of one barium is appearing, one sulfate is appearing, one barium and one sulfate. Okay, now you have two sodium pluses and two OH minuses, so you have to count with 2 here, right? So the two equations are balanced now. Writing balanced chemical equations, right? That is done. The second step is done. First identify the goal, then coming up with the balanced chemical equation. Third thing, the third point, coming up with the simultaneous equations, with the use of data points, See, let's try to come up with the simultaneous equations. So what are the data points available here? See, the first data point we can see here is actually appearing with this value, no? Appearing with this value. See, with the barium hydroxide, right? This volume and concentration data are given, so that those data can be used to come up with the number of moles of barium hydroxide. That is one data point with the barium hydroxide, right? This is the one data point, first data point, right? So what is the other data point appearing with this question? That is this mass. It is the mass of the precipitate. So basically simultaneous equations can be written only for masses or only for moles, right? Not for other stuff. You can't write simultaneous equation for just for milliliters here, right? Okay, simultaneous equations can be written only for masses or number of moles, right? So this is first data point. This concentration and volume data will give you the number of moles of barium hydroxide, and the second data point is this. This is actually representing the mass of the precipitate, right? So let's write the two simultaneous equations, right? So first one is for the number of moles of barium hydroxide, right? Moles. See, so first of all you need to come up with in terms of x and y, and at the other side, right, you need to write the data point, right? So let's come up with the data point first of all, right? So BaOH2 moles. So your concentration, if you have to multiply the mole DM minus free value with the DM free value, is 20 into power minus 3. The volume in decimeter cubes will give you the concentration, that is 14 into 10 minus 3, that means 0.04 moles. Actually that is equal to what? You are with x moles of this one, and y moles of sulfate, sodium sulfate. So what we need is not this sodium sulfate or sodium phosphate. What we need is actually barium hydroxide and barium hydroxide moles, right? So x moles of this thing means x is for 2 portions. We need such 3 portions. So x moles is for 2 portions. So divided by 2 will give you for 1 portion, and we need such 3 portions. So 3xO2 is the amount of barium hydroxide which will consume total react with sodium phosphate. What about this? This is 1:1 ratio, so it is simple. So y moles means here also y moles, right? So the amount of moles of barium hydroxide in terms of x and y is going to be 3 by 2x plus y, which is going to be equal to 0.04. Normally the simultaneous equations should be kept in the linear form, so that it is better to multiply with this thing with 2. So it will give you 3x plus 2y is equal to 0.08. Take this one as the first equation. 3x plus 2y is equal to 0.08. just take that thing as the first simultaneous equation. Right. Let's come up with the second simultaneous equation. Second one. Right? Okay. That is for the mass of the precipitate. Mass of the precipitate. Right? Your precipitate is this. The combination of these two guys, right? So let's write second simultaneous equation for the mass of precipitate in terms of grams. So we need to convert these guys to mass. First of all, we can come up with the number of moles there for these two precipitates, right? So as you are with x moles here, this should be x over 2. So 2 to 1 ratio, no? X moles means x over 2. This y moles means this is also y moles, because 1 to 1 ratio, no? 1 to 1, right? So to convert this number of moles to grams, first we need to multiply these things with their g mole minus 1 values. So first of all, we need to come up with g mole minus 1 values. So molar weight of barium phosphate, right? So what is that value? Molar weight of barium phosphate. So barium into 3, 137 into 3, 137 into 3, right? That will give you 300, 411, no? 411. And phosphate 64, 16 into 4 is 64, and 31, that is 80, 95 into 2 is 190, that is 601. So molar weight is 601. What about the molar weight of barium sulfate? 137, and here 64 and 32. 64 and 32 is 96. With 137, it is 233. Right? Okay. Right. Now we can convert the x moles and y, these number of moles, to the masses. The total mass means the mass of this thing plus mass of this one. The mass of this thing can be written as number of moles into its g mole minus 1 value. That means x over 2 into its g mole minus 1 value, 601, plus is y into 233. Right. That value is equal to the mass of precipitate, that is 8.34. Right. If you are to come up with the linear form, it could be written as 601x plus 466y, that is equal to multiply by 2, right? To come up as linear form, right? So that will give you 16.68. That is equation number 2. Equation number 2, right? So two simultaneous equations are done. Let's come up with the solving part now, right? Let's try to solve this one, right? So I'll from here solving. Right, for x and y. Right. So what we can do? So you have 3x and 2y, the stuff are there. So let's equalize the coefficient of y. Equalize the coefficient of y. So equalize the coefficient of y. You can multiply this thing with 233. That will equalize number to 466, right? So just multiply with this in 233. So with that, right, with the 2 to the 3, this is going to be a larger number. So let's take like this. So let's multiply the 1 with 233, then minus 2, right? So that thing will get rid of y. So multiplying the 1 with 2 to the 3 will give you 699, no? 233 into 3, 699x minus 2 is 601 x, that is equal to what? Equal to, right, this into 2 to the 3, right? So 0.08 into 2 to the 3, let's come up with that value. 0.08 into 2 to the 3, the value is 18.64, that value minus this value 16.68. So this will give you 98x is equal to, right, 98x is equal to this value. This is 1.96, no, 1.96. So x is going to be equal to 0.02. So x is solved. So you can use this value in here at the equation 1 to come up with the y. From 1, you could say the y is equal to, x is 0.02, so 0.02 into 3 is 0.06, and so 2y is equal to 0.02, so y is 0.01, right? So those things are done. So solving is done for x and y. So finally achieving the goal. That means achieving the concentrations. So what we need is the concentration of those two guys now. So the concentration of sodium phosphate can be taken as the number of moles of sodium phosphate, that is 0.02 moles, divided by the volume. The volume is 25 cubic centimeters, right? So just divide by 25 cubic centimeters, 25 decimeter cubes, right? So volume should be written in terms of decimeter cubes for the concentration. So it is going to be what? This comes up as 1000. So 1, 2, 3. It is going to be 20 or 25. 20 or 25 is 0.8. Right now, let's complete the stuff with the sodium sulfate as well. Concentration of sodium sulfate is actually the amount of moles of sodium sulfate, this is 0.01, divided by the volume of the solution. The volume solution is 25 cubic centimeters. That means 25 into 10 to the power minus 3 decimeter cubes. So it is going to be, right, 10 or 25. That means 0.4, no? So those are the two concentrations, right? So that is actually we have achieved the goal, coming up with the two concentrations, right? So let's complete the stuff now. Complete the note. Right, no. So we can conclude at this stage. At this today we have discussed about the precipitation reactions. right, how to use the precipitation table to write the precipitation reactions, and we had discussed about the balancing techniques. Then we had used those knowledge we have gathered to solve some simple calculation questions, right? So that is what we have done today. So, and we'll wind up at this stage, and we'll meet with the next type of reactions, the redox reactions, next day. Until then, goodbye.